think I'm sharing my screen okay. Okay, so today we'll be actually continuing from last time. And so last lecture and this lecture, I've been kind of emphasizing it last time as well, that it's a mix of both learning and decision making. At the end of the day, learning by itself, is useful, but you want to kind of apply it, which is kind of make decisions, right? So we have been looking at last time a particular format, a particular setting of such learning and decision-making loop, decision-making setting, which is actually this for loop, where you learn a little bit, you make the decisions, you kind of learn how your decisions fared, as in you get feedback on how your decisions fared, and then you again learn, okay, maybe I should not take these actions, maybe I should take these other actions, and you keep repeating that. Okay, that's called sequential decision-making, and that's where that's what we focused on. There are many other types of decision making. Like, for example, in contrast to sequential decision making, there is this whole kind of area of batch decision making, or whatever, one shot decision making, where, for example, if you're doing a large infrastructure planning project, so there will be some forecasts, economic forecasts, climate forecasts, and all that, but all that feeds into one big design decision, or it could be financial decision on what the project will be, right? So what the details of the project will be. So those types of decisions are not what we're looking at. So we're looking at sequential decision making. And last time was the simplest setting where we did not even have feature vectors. So if you really want to think of supervised learning, where there's no feature vectors, what are you estimating? You're just estimating the expectation of Y. Like, think of a target. If you remember from ML 575 class, you're typically predicting the expectation of Y given X. Right? So if you think of a statistical model there, or probabilistic kind of representation of X and Y being random variables. So last time, if you want to kind of relate it to supervised learning, we did not even have X. So we just wanted expectation of Y. The only difference was that it was not Y, it was actions, A's, or whatever, decisions, if you want to change the symbol. And all we wanted to know was, if there are multiple actions, we just want to know expectation of whatever, decision 1 and decision 2 in terms of how rewarding they will be. And if we knew those expectations beforehand, then obviously we'll take the better decision. But if we don't know the expectations, we have to kind of estimate them. And while estimating them, you can do A/B testing. You can spend some effort. You keep trying out decision 1 for 100 times, you'll get a sense of how good decision 1 is. Keep trying decision 2 100 times, you'll get a sense of how decision 2 is. And how to do better than that. That was the whole business of multi-armed bandits. And towards the end, we were talking about contextual bandits. So I'll discuss that in a second, but let me just come back to where we are. Yeah, I mean, sorry, I know I'm jumping back a bit here. So we're here. Next lecture, choose the slots on that Excel sheet, and the reports are due in a couple of weeks. Okay, and then it'll be in-person presentations in the classroom on 24th. Okay, so with that tangent, let me come back here. Last time we were talking about this, right? So as I said, if you don't know the value of how good addition is, you need to estimate. That's the learning part. And we looked at A/B testing, then we looked at multi-armed bandits as situations where there's no feature vectors, just want to learn whether action A is better, action B is better, and how to do that in an interesting for loop way, this online machine learning loop where you take an action, you get feedback, take an action, get a feedback. How do you kind of use that feedback in an adaptive way to kind of prioritize actions which seem more promising? Okay. And then towards the end, we looked at contextual bandits. Very crudely, if you want to understand why there's a new name, contextual bandits, it's just supervised learning. I mean, you could use a supervised learning approach in this online loop. If you remember, you can always do, okay, if you had 100 data points, you can fit a model which kind of predicts Y given X. Then if you get the 101st data point, you can add it to your data set. You can retrain your 101 data point data set and again get a model which predicts Y given X, and so on. So you can actually, as long as you're accumulating data, which is what you would do in an online machine learning setting, you can always augment your data and retrain your model, or you could do incremental training. So there are many different things you can do. You can always do supervised learning, but supervised learning is not enough. And that's why this new name, which is very different from supervised learning, called contextual bandits, is because you have to do exploration and exploitation. Okay, and that's what we learned without, when we drop the features part, there's still need for exploration exploitation. So clearly, when you have feature vectors, you do need exploration exploitation. Okay, So that's the kind of the reason why there's a different name. Although the heuristic I mentioned where you could just use supervised learning, it doesn't work if it's really in that setting. So I'll point out more the differences between supervised learning and reinforcement learning today. But all the things that we saw last time are also elementary reinforcement learning problems, okay, which is like simpler reinforcement learning problems. So today we look at, let's see how much we can cover, but we can look at basics of reinforcement learning. We might even get all the way to, we can skip some parts and get to one algorithm, because each part we've been covering, we have at least one algorithmic approach. So we can look at, if possible, we'll look at one algorithmic approach called Q learning. It's a very 30 plus 40 years old algorithm, but still, has a very good aspect of acceleration exploitation, which has to stay, which given last week and this week, but also some other ideas which lead to really good performance in sequential decision-making settings. Okay. We'll not have time for Atari games and AlphaGo and all that, which we had examples for. And neither will we have a time for ethics, fairness, accountability, transparency, and sustainability, which are very important topics. Maybe there's another course. I don't know if you're going to be here next semester, but there could be a course on this. Special topics course. I don't know. I'll check. But it's an important aspect of, especially with AI becoming more and more prevalent in common life compared to, 5 years ago, for example. Separate course, no, but I know that there's been discussion in curriculum design. I know there was a proposed course. I don't know if it's in what the format is. Yeah. Yeah. But there is a course on this. Yeah. Yeah, I can update. If you send me an email, I can tell you what the details are. Okay, so yeah, so I want to actually, before I get into slides, I do want to mention a couple of things. Last time, at least in terms of motivation, although I'll probably not talk about motivation. So this is an example I just got, from somewhere, but this is what the researchers, in this case, DeepMind, I guess, they were training the agent to play this game. Okay, so this is called Breakout, and what is the action? The action is just to move left and move right, or stay the same. I mean, it's basically joystick action. So whatever is a discrete number of actions, and you have to balance the ball. The ball goes up, takes a brick, and so you get increment in points. And here it's learning from getting a context. Okay, so it's again closer to supervised learning. The context is going to be the image. In fact, the screenshot of this game. Okay, so it's as if humans, we are looking at the screen and then we're deciding what to do. It's exactly what the agent is also doing, or the software is also doing. You're getting a screenshot. In fact, there's some more details. It's not just a screenshot, but like 3 copies of the screenshot, as in screenshot and the previous screenshots. And based on that, it's just trying to decide. Okay, so it's trying to decide whether to go left or whether to go right. And it has to explore and exploit. So in some situations, maybe going left is promising, but if it has not tried going right, then it doesn't know if that actually might have led to more bricks getting cleared. Okay, so there is this exploration exploitation part. This is just the initial part of the game. So after quite a few number of episodes, which is this one, it actually figures out a really smart strategy, which you could also figure out, like if you play it for a few minutes, which is this, right? You send the ball up through the thing, and it clears a lot of points for you, right? And not just one time, like you really focus on sending it over there so that it clears as many bricks in one go as possible, right? So how does it do it? Exactly right. It's trial and error. So reinforcement is all about exploration, exploitation, which is actually another way to say trial and error. You have to try things so that you learn about it. Okay. In supervised learning, there's no such notion of trying something else. Okay. And you may say, okay, this seems very esoteric, as in like, what is the real world application? Like games is fun thing. Think of recommendation systems, right? So let's say you have Netflix or Amazon and whatnot, where you have a context, or MSN.com example from last time. You have a context, you show something, there was some feedback, okay, it's purchase or not. You don't know what would have happened if you had shown something else. Okay, so you can't let's say in this process, you showed user came with some profile, you showed something, some reward happened. That data is not enough. I mean, you can always build a supervised learning model, which can say, given this user context, what to show. But then you already know what to show. Like you already have a policy. What is the point of learning a supervised learning model there? Okay. Then you may say, oh, instead of figuring out what to show, I can say, given the feature vector and what I showed, can I predict the reward? You could do that. That could also be a supervised learning problem. Even that is not enough, in the sense that you only know what happened for the thing that you showed. You hope that there is a generalization where if you change what you showed, perhaps you can get a better reward. And this whole idea of contextual bandits and reinforcement learning is about that. So what would happen if you showed something else? Okay. Instead of just generalizing, relying on a function to tell you maybe this would have happened, you actually try that, and maybe you get some samples of what would happen. I mean, I'm not saying you try every single action in every situation as possible, but there is some scope for you need to explore to kind of learn if something else is better. Okay, that's a key idea here. And here's another one, which I don't know if I've shown you before, but I'm trying to avoid the videos that we saw last time. So this is another game. I don't know how many of you played this game. A few of you tried this game. So this is Flappy Bird, or a clone of it. Basically, here again, it's the same idea. It's a question of when to hit one of the keys or spacebar. And again, the input is this visual, and the output is a action of when to hit the spacebar. And it's learning. And this is just a video where it has already learned how to kind of avoid the tubes. Okay, so this is again a situation where you have to explore and exploit. So you don't know when to jump. At least the algorithm definitely doesn't understand like the physics of it at all. We didn't tell it like what the physics is. We just try if you, the only feedback actually in the previous game thing and this one is going to be this number. Is this number going up, going down, or did you end the episode as in you got, killed, right? So to get to these, these are just short demos, and the same idea translates to advancements in ChatGPT, okay, and Gemini and all other types of LLMs. And this is actually a blog post from Hugging Face. I think many of you are probably using it for data sets or pre-trained models. If you haven't, you should use it. This is from 2022. So in 2022, OpenAI's researchers proposed or kind of published this idea that you can actually improve an LLM by not just doing next word prediction. Remember in our NLP sections of the course, we said, okay, why can't we just do translation, or like we briefly talked about BERT. BERT was not really predicting next word, but basically predicting masked words or fill in the blanks type of a problem. But you can imagine, doing some next word prediction. But at the end of it, you actually get an LLM, which can, given a bunch of words, can give you a distribution over the next word that can happen. Okay, that's what a language model is, right? So the idea in 2022, and this is what I showed last time very briefly, was the idea of reinforcement learning from human feedback to further improve the LLM. Okay, so let me just go down to that image. So this is what you would do, right? So this is what we've discussed in previous lectures. We have some data set, it doesn't have to be even prompts, actually, this is not what we did. Okay, let me actually go to the figure that we saw last time. So last time, this is the figure that we saw very briefly, where you have some data set. It's called prompts data set here, but you can imagine you have some data set, text corpus, and all you're saying is, okay, can I predict the next word? You can always build a language model. You did that with very simple language models in your LSTM-based language model in your assignment. You can build a language model, and then you can further improve it by saying, okay, for a new prompt, what all types of responses, what all different responses it can give. It can give multiple responses because it's stochastic, right? When decoding, you can always decode by flipping a coin and picking a word from that distribution of words, right? At every decoding step. So you can get multiple responses. You ask humans to score it. and get a rating of, okay, response 3 is better than response every other response, response 5 is better than everything else remaining, and so on. You get a ranking, and then use that ranking to build, for example, a simple prediction model of given a response, how good it is, how much humans like it, and then use that model to further train this language model. Okay? And that further training process is wrapped up in a reinforcement learning approach, okay, where the language model tries something. The language model tries something in a sense, it produces a response, it gets a feedback saying this response is not, good or bad in some scale, right? So this reward number is generated. Based on that, next time for a similar prompt, it's gonna try to avoid low reward responses. Okay, so that's how human annotated data, preference data, is captured in LLMs. Okay, and with pretty expensive exercise, it's not like a few people annotate and give this results. It's mostly a lot of people involved. So this is a more real world use case of reinforcement learning being used. You don't have to use reinforcement learning. There are multiple approaches for many things, but once you deviate away from the canonical reinforcement learning setting that we're seeing, but they propose this, and there have been variations of this, not just this, but like other ways to use preference data in today. Here's another one, right? So this is this is actually about reinforcement learning for robots, where they mix, in the title itself, you can see they mix transformers and a reinforcement learning algorithm, which we'll see, called Q-learning. And they say, okay, how to do that, how to use that for kind of training robots. Okay, just to give a sense of what's possible. So before we actually get into the content, I also want to show one demo, but maybe we can do that during the break so that it's a little bit lighter. So the demo is going to be an example of actually Q-learning code. It's also there in our examples subfolder in our repository, but I'll just run it just to kind of give you a sense of what that code is. If you want to play with it later, just understand, we'll do that. Any questions about whatever I said? It's all been kind of not very precise. So let's actually get into the slides. Just drop this. So today's outline, we'll probably skip the first bucket. I've been talking about complex decisions, or decisions which are not just simple transformations of your prediction. Okay, so there's some situations where decisions are generally a simple transformation of prediction. Let's say you're only focused on one stock in the stock market. Then let's say you're forecasting returns for that stock. If you're forecasting tomorrow's return is going to be high, then perhaps you buy the stock. Let's say you're deciding, you're only going to buy 1 unit of that stock, right, or an asset. Then there's a very simple transformation from forecasts to decisions. Okay, there's nothing else going on, like a threshold, right? If predicted returns are going to be high tomorrow, then perhaps you buy now. If predicted returns are going to be low tomorrow, you sell now and perhaps buy tomorrow. Okay? So something like that. But the moment I'm just talking about decisions where it's not very simple transformations of your predictions to decisions. Okay, so that's what the first bullet point is talking about, and these include all the real world problems like inventory management, routing, staffing, all sorts of specific real world problems. So I'll skip those slides. Yeah, so I'll directly get to where we stopped last time. Okay, as I said, the idea is to mix decision making and predictions, and we start with the simplest starting point where all we didn't know was that there was no features. All we wanted to know was whether action A is better than action B. Okay, and if you already know action A is better than B, then just take action A. There's no need to learn anything. Okay? Now the learning only comes because I don't know whether action A is better than action B or action B is better than action A. And how do you learn? You have to try both of them. Okay, that's the exploration part. In the sense, you can't just settle on one and just go on with it. So you have to try both, but you have to try both in an efficient way. You can't be spending like an A/B testing situation where you can't be spending 100 times take action A, 100 times action B. You can be more efficient than that by relying a little bit more on the promising action more and more while taking into account that you need to explore. What does that buy you? It helps you minimize your cumulative regret. So during the time that you're learning, in hindsight, there could be one of these actions is best, maybe action A is best. At least you won't regret that you did not take action A too few number of times. In the sense that if action A was promising, your adaptive algorithm, this multi-bandit algorithm, would probably kind of pick action A more often. And so in hindsight, you're not too far away from what you should have done from the get-go, which is to take action A. So that's the key metric. That's the way we are measuring the performance of these approaches. Okay, so you have to explore and exploit, but you want to kind of minimize cumulative regret. Which regret just means what could you have done in hindsight versus what did you actually do. So that gap should not be too big. And we saw some curves which are like sublinear, as in things that they don't go as a 45-degree line or equivalent, but something which kind of tapers off the cumulative regret. So you should look at those slides to get a sense of that means good in the sense the algorithm is learning. Okay. So we saw several algorithms. I'll not get into the details at all, but you'll see that the epsilon greedy algorithm, the simplest one, where you're saying you flip a coin, try the most promising action now, or if the coin lands tails, then try random action, okay, uniformly at random. Okay, that simple algorithm is also going to be part of algorithm for reinforcement learning called Q-learning. Okay, so which is a really good algorithm. There are many algorithms, but let's stick with one for much of this narrative. So that's the first row where there's no feature vector or context or state. In the second version, there is a state. So you get to see the state as in a context, and then we need to decide on an action. So this seems like, okay, the input is a vector, the output is an action, which is potentially, let's say, 5 actions. It's discrete, so it looks like a multi-class classification setting. And it is, in a sense, the function here could be like a multi-class classifier choice also, except that you need to do exploration exploitation. So that's important. And once you take that action, both the action, what did you decide, under what context determines the reward. Okay, that's kind of pretty natural. So what's the situation and what action you took together determine what reward you get. And hopefully you remember what reward you got to next time be, maybe that action is promising, then you double down on it perhaps a little bit. If the action is not promising, maybe you don't, you try to avoid that action. Okay, so that you can still take care of the cumulative regret, metric. So that's contextual bandit. So it's very similar to supervised learning, except you need to do exploration exploitation. And so the algorithms, but the probably guaranteed algorithms, and guaranteed in terms of cumulative regret being low or sublinear, they do rely on supervised learning as a step in there, but they do a few more things to ensure this correctness and stuff. But at the very high level, as I said, the difference between contextual bandit and supervised learning is all about you need to kind of try something else to know what you missed out in terms of actions rewards. Okay? You can't just predict the actions reward and not do exploration. Okay. The next setting, which is what we'll, the basics that we look at will cover, is the situation where the context influences future context. So as in your actions influence what's the next context you see. Okay, in the sense that let's say you're a website, and since we've been mostly talking about marketing here, your website is user who comes in, sees the recommendations are really bad. It's going to influence whether the next time what their favorite, whether they like your website or not. Okay, tomorrow and day after tomorrow. Okay, maybe you can, there's a longer term impact, or there's a future impact of your actions today. Okay, that's not there in supervised learning at all. So your rows are permutable, like everything is IID. But here, what action you take today has dependence on what you'll see tomorrow. Okay, so the whole process is not IID at all. So it's dependent process. Okay, and we'll look at a specific dependent process. It's a Markov process with just some, which simplifies things, but we'll look at one such dependency. Okay, so that's the RL setting that actions have future consequences. But in addition to that, the rewards for the action could be arbitrarily, could be many days later. Okay? So generally in multi-unbounded and contextual bounded, you take an action, you kind of get a reward immediately. So there is no like a delay in terms of reward. Although there is some people have extended the first two rows into the situations where there's delay and reward. But third one, there's really, there could be like a sequence of actions that lead to like a huge reward later. For example, you studying a lot about deep learning might have a huge reward later, right? So, but immediate reward may not be too much. It may be painful, maybe, consuming a lot of your time. You're not able to go out and party, whatever it is, right? So those are the two aspects. So I will also introduce another thing while we talk about overview, is that we're talking about reinforcement learning as a setting in sequential decision making, where we do both learning and decision making, right? That's the whole point of this. But there's a version of this problem where you don't have to learn. Let's say you knew everything about the world, as in you knew, oh, if I take this action, what reward I get? If I take, what's the different states that can transpire and so on, or what are different feature vectors that can transpire. Even if you knew everything, okay, how to make decisions is also an interesting problem. Okay, it turns out. I mean, we'll see that in the next few minutes of why, and that problem is just what is called a planning problem, okay, or just a decision-making problem. Obviously, if you drop the learning part, there's what else is left, right? Decision-making. In particular, people call it the planning problem typically, and you'll see that by thinking about the planning problem and the situation, which is RL, where you have to learn and plan, you kind of you learn like what the differences are. Okay. It turns out the planning problem is interesting in the sense that it's not a trivial problem to plan. Okay. So planning itself is hard. On top of that, we have to learn. So there's like a pretty complex thing. That's what happens with the robots thing I was just showing, or the Atari game example that I showed, or full self-driving like we saw last time. There's planning and learning happening, okay, which is RL is happening. So, but you can imagine if I knew everything about the world, still to decide, where the car needs to go. For example, it has to merge into the highway and exit at, take some exit and take a run, take a right. That's still, even if you know everything, to go from point A to point B, you need to still figure out how to do it. And that's the decision-making problem. That will not be trivial. Okay. With that caveat, I mean, I'll come back to this planning and RL again and again. Actually, I think I've missed something, which is I wanted to briefly mention what the goals are so that it's clear, like by the end of the session, what do we learn? Yeah, the goals are modest. Okay, so it's the first time, perhaps for many of you or all of you, it's the first time you're seeing reinforcement learning. We just want to understand what is reinforcement learning. It's online machine learning loop. Okay, it's a sequential decision making loop where we learn and also decide. Okay, and exploration is a key part. On top of that, for the full reinforcement learning setting, there is some properties like your actions have future consequences, and your rewards for your actions can be arbitrarily delayed in time. So there's a temporal aspect to this. There's also across actions you need to explore and exploit. Okay, that's essentially what reinforcement learning is. But as I said, the data is now going to be not IID. So particularly, we'll look at some way to kind of capture what is the type of data set that we're getting. Okay? So one of the models is just again, it's a model. It's not reality, but it's a model to describe the setting. It's called Markov decision process. And once we understand the basics of what is the Markov decision process, it'll become clear what is the planning version of the problem and what is the actual reinforcement learning version. Okay. Planning version of the problem is where you know everything about the parameters of this stochastic process or whatever this random variables are, like distribution and things like that. And you still need to figure out what to do in which situation, in each state. Okay. That's the planning version. In the in the reinforcement setting, I don't know what's going to happen when in each situation if I do something, but I still need to figure out what is the best actions to take. Okay. And the third goal is just a few keywords. What is the policy? Policy is just going to be a function from states to actions. What is the value function? That I will not tell you now, but we'll look at what is the value function. And they are related to each other. And so we'll look at what these are, and hopefully by the end of the lecture, you'll appreciate what is a policy and what is a value function. And if we have time, we'll not look at the next lecture's goal, but just a second point, if we have time, just because that's kind of caps up like an example of a practical algorithm that you can just any setting, we'll see an example setting which is in this other tabs, but any setting you can just apply that algorithm. It'll only work for toy situations unless you're clever, which is what was the whole advancement with that breakout game, and they were actually applying just Q-learning. It's just that they were using CNNs. Remember the screenshots, so they have to kind of process images. So they were using CNNs in between on that algorithm description. That's all. That's to do that in 2012. When GPUs were just getting bigger and bigger, and data set was available, and computers were getting better, and that's the big delta in 2012. In addition to the ImageNet improvement with CNNs the previous year. Okay. Okay. So. Sorry, I just want to mention the goals. So let's come back to RL. RL, as I said, it's about sequential decision making. So there are going to be three components. There are going to be two components: an environment and an agent, and they interact with each other. And as I said, one of the key aspects is going to be that we did not see last lecture is that your actions, your decisions, or actions influence future contexts, okay, or states. That was not there last time. There was in contextual management, the states are just independently realizing. Users' profiles independently realize, depending irrespective of what you do. And as I said, the second thing is agent can get a potentially delayed feedback signal or a reward based on what they did. Okay. And the objective is very similar to last time. We want to kind of keep selecting actions, do trial and error, while during that interaction, or basically learn what actions take in each situation or each state. Okay? How to select actions to maximize what reward I can get. And also, obviously, if I'm doing trial and error from a point in time, so perhaps there are a bunch of interactions going on. Over those interactions, I hope I collect more and more reward, as much as reward as possible. Okay. So it's very similar to, I'm not saying something about cumulative regret here, but there's a way to formulate it as a cumulative regret objective as well as you want to get lower and lower. You want to have the regret taper off, basically. Okay. So RL is that problem. So what is the environment? Environment has to it's an API. I think of a API as in like a function, right? The function as an input and it produces a sum output. Okay. So if you want to think of environment and agent as two functions or two blocks, then let's focus on the environment now. Environment just has two inputs. So it has one input, actually. It just looks at what did the agent decide to, what's the agent's action. Okay. So the environment is really our way of defining, okay, what is the world in which the agent is operating. Okay. So for example, the simulator for the Atari game is the environment. All it has to say is, okay, given this action in this state, if it is given an action, like the agent gives the environment an action AT, and whatever the state it is in, currently let's call it ST, it's going to move to a new state ST plus 1 and spit back a reward RT plus 1. Okay, so if you think of a function, input is an AT, it just says, oh, input is an AT, current state is ST, and new state is ST plus 1, and spit out a reward RT plus 1. So that's all it's doing. If you want to think of it as a function. Okay. Now, what is ST, AT, and RT? AT is going to be the action. So this is a capitalized letter, mostly trying to represent that this could be a random variable. ST plus 1 is the next state or the next future context. Remember, your actions influence future. So that's why it's we are indexing it that it's ST plus 1 and it's related to ST. And reward is RT plus 1. So this indexing is just AT leads to next state, a new reward from the current state. The environment is really some sort of you can describe the environment using some sort of a process. Okay, process is a technical word in applied probability. It just means a collection of random variables. A stochastic process is nothing but a collection of random variables. Okay, these collection of random variables could be independent, right? So if I flip a coin, so x1, x2, x3, x4 could be random variables representing Bernoulli. Could be Bernoulli distributed. And they could be completely independent of each other. That's still a collection. of random variables. It's still a process, stochastic process. It's just, independent. There's no dependency across time. Okay, but in general, there could be dependency across random variables. Okay, so that would be a dependent process. And the process that we'll look at today is called a Markov process. And so the environment behaves in a Markovian way is what we can assume. And there are ways that it is not true also, but we can assume for today's lecture that it is reasonable to make this assumption, okay? Which is that the random variable st plus 1, whatever its distribution is, given all the previous random variables, only depends on the most recent random variables realization, okay? So it's basically saying that given present, future is disconnected from the past. I mean, this is probably something you've heard in other lectures, perhaps. So this is what the environment is going to capture. Okay? It's basically a stochastic process. It's given an action. It's just telling you what's the new state you're going to go in, and here's a reward that if your action was really good, here's a huge reward like $100. Action is really bad, 0 or -1 or whatever it is. Yeah. What is the agent? Agent is again a function, and this is what we're going to try to build. The Q-learning approach, or that I was kind of briefly alluding to, is an algorithm that the agent can follow, and therefore hopefully do well in terms of collecting rewards and learning and doing trial and error in a principled way. Okay? The agent, basically what it does, it's basically the online machine learning loop. So it looks at the reward, what's the new state, which is the third step. So third step, if you recall from last time's for loop, look at the reward. First step is to get the next state, and then the middle step was to take an action. Okay, that's what it does. That's what the agent does. So look at the immediate reward that you get, put it up, I guess collect it with all the rewards that you've gotten so far, and use that information and perhaps all the states that you've seen, that information, to hopefully take intelligent actions next time. Okay? That we are not getting into yet, but we'll get to that. Hopefully take better and better actions through Q-learning approach, for example. Here we're just saying that the agent's objective is to maximize expected rewards. Okay, so a lot of things are hiding in this notation. So we'll come back to these types of notation in a few minutes. Okay. Agent's action affects what it sees in the future. This is what I said. So if I take action A, I might get to, let's say, for example, right? I mean, if I take exit 1, I might get to, town 1. And if I take exit 2, I go to town 2. If my objective is to go to town 1, then I'm kind of, there's a different reward for taking different actions, right? So one of the things is exactly this, right? So temporal trading off, that you could trade off current reward for potentially getting a better reward tomorrow. So you being here and not outside playing, has lesser reward right now, perhaps, but maybe hopefully a better reward tomorrow. Okay. So those are two key objects, the environment and the agent, and they're just interacting. And the interaction, one of them is just the feature vector, right? The state. The other one is the reward signal. Okay. The reward signal hopefully captures all the incentives that the agent is trying to optimize for. Okay, so it's called reward hypothesis, whether it is always possible for any task to have like this scalar signal capture the intent of, capture feedback in the right way such that the agent can optimize that and therefore achieve the task, complete the task. Okay, there's a little bit of gap there, whether it's always possible to provide some reward signal like that. But in general, that's the only way the agent is able to learn whether that's the only feedback it's getting. So unlike supervised learning, right? So you predict dog, and somebody says, "Hey, it's not dog; it's actually maybe a fox or a cat or something." So the reward is different there. Okay, so you are actually not just know that you made a mistake, but you also know what the correction was. Here in reinforcement learning, you take an action, it just says, "Hey, it's wrong." That's it, right? So for example, like the reward could be saying $0, you made a mistake. Now you have to go back and kind of try different things, perhaps, to figure out, okay, maybe that for that image, maybe it's a fox and not a cat. Okay? So your only signal is not is only a reward signal, is what I'm trying to say. It's a scalar signal. As I said, the goal is to just take actions to figure out to maximize total future reward. I'm using the word future reward, but it's basically you need to figure out how to learn and earn, as in earn rewards, and so learn enough about how good the actions are in different states. So let's look at the picture, right? So this is what is happening. So agent on the left, environment on the right. Given the current state and maybe a reward from some previous action that I took, I get that, I accumulate that information, and then I have to take an action. So I'm not saying that this action only depends on these guys, but this action hopefully becomes you're getting smarter and smarter, and you take better actions next time. Okay, so take some action. Environment says, okay, given that action, here's a new state, a new reward, and then take some other action, and so on. So that's the loop here. Okay, this is exactly the online machine learning loop. Okay, so the state is like the feature, optional feature in step 1. Action is the action decision making step 2, and then the reward is step 3 in the online machine learning loop. So it's exactly the same, except the long-term aspects and things like that. Right? Any questions here? Okay, so as I said, I did mention about the reward signal. So supervised learning at the top, you have training signal is basically for every feature, what is the right thing you should do? You already have that. So it's a batch of data, or you could kind of collect the data again and again and incrementally train your model. And that blue box is just given an input, new input, and just trying to predict the target as accurately as possible. Whereas in reinforcement learning, you have, let's say you have a similar input, let's say images. Okay, you produce some output which are explicitly should be actions. They cannot be just labels, right? So they have to be actions. Those actions impact. You can make those actions in the environment, like picking a stock or moving your robot, left or right, or moving the car, whatever. And the environment gives back a signal which is not what is the right action to do. Okay, if it said, hey, this is the action you took, this was the right action to do, then that's not really reinforcement learning. Okay, you take some action, it only tells you, hey, how good that action was in that situation. Okay, so it's kind of limited, and you have to use that to kind of learn. But also, it's not just that, but environment will also tell you what the next input is. So it's really a strong dependency. So the moment, if you're going down the wrong path, you will kind of see those types of contexts, those types of states. Okay, so you can't figure out, okay, for what is so your data collection process is very biased, is what I'm trying to say. So you can't really do supervised learning here, right? So you'll see certain types of inputs depending on your current actions, and you'll never probably be able to jump across and see some other types of inputs. Okay. Let's come back to that in a second. As I said, there are two things, environment and an agent, and they interact through exchanging the states and the rewards. Now, let's get into the agent. Let's open up the agent. Okay, so at least kind of understand how to design an agent. Okay, we are baby steps to design how to design an agent. And for that, we want to introduce a couple of concepts. Okay, a notion of a policy, a value function, and a model. Okay, these three are all related, but these three components are ingredients to design an agent's strategy. Okay, so the Q-learning algorithm kind of works with something like this, some of these stuff. So it's good to understand what are these building blocks. Okay, so we're not worried about learning or decision making right now. We're just, as in like, we're not trying to design an algorithm yet. Okay, we'll design an algorithm way like an hour later, at least. Right now, don't worry about the algorithm. But to think of any algorithm, you need to kind of understand these are the most basic building blocks from which I can design some algorithm later. Okay. What are these building blocks? They're just concepts. So the first one is pretty simple, a policy. Policy is nothing but, so this is just to kind of formalize our, how to define an agent, agent's in policy, right? So agent's approach. So a policy is just agent's behavior. It's just saying what is that you're going to do in every state or every context. Okay. So this is so RL is all about searching for the best policy, right? So what is the best thing to do in every state is if I knew what's the best thing to do in every state, I don't have to kind of do any learning. In fact, I've already solved the decision-making problem also, right? Slight difference is minor detail is that a deterministic policy, you say every state, what is the action to take? A stochastic policy will say in every state, here's a distribution over actions, and you can pick some action if you want. So there's slight difference in the notation is just pi of S and pi of A given S. Pi is just the representation for policy. So you can think of this as like in supervised learning world, the F function we keep using, that's what this is, except that the output of the F function is actually an action. like a label, equivalent to kind of a more of a classification setting if you want. Although there's a whole, you can have continuous actions also. So you could have, move 2 inches or 2.5 inches or whatever, like if you have drones and things like that. So you can have continuous actions also. So that's what a policy is. So here's a very simple example just to kind of illustrate what a policy is. No algorithms. So here's an environment. This is called a maze, right? As you can see, you just have to figure out how to go from left to right. That's the setting, but we'll not figure out how to go to left setting. We just want to define what a policy is. And the policy is something like this. It is exactly the same picture where I put in red arrows. The red arrows just say what an example policy is. Okay. So an example policy is saying in every state, what am I going to do? So this picture, it's nothing deep going on here in the bottom right picture. All I'm saying is in every state, what am I going to do? I'm going to go top. I'm going to go north. I'm going to go east, west, or north. Okay. So that's an example of, this is a visual representation of policy. Okay. And this seems pretty elementary if you've already done like machine learning, but just kind of want to ground this. Okay. So for example, if I flip this arrow here from going north to going south, that's a different policy. The only difference being in one state, it is a different, it's taking a different action. Okay, so next let's look at something new, actually pretty new, and we'll spend some time on this, is the notion of a value function. Okay, a value function is a function, as its name suggests, is a function that gives for every state, every white box that you saw in the previous maze. Every white box is a state, by the way, or a situation. For every state, it assigns a number. Okay, so that's what a value function is. And as the name suggests, it assigns a number which says how valuable it is to be in that state. Okay? Forget about actions, forget about policies, forget about your approach. This function is supposed to tell you how good it is to be in some state. Okay? So for every state, there's a number. So you can imagine, you're doing something in that maze, for example, but you went to a really, random corner, which is like pretty far away from the exit. The value of being in that state is like really low. Okay? And perhaps, wherever the exit is, maybe the few states around it, the value of being in those states is pretty high. Okay, so that's the idea that this function is trying to capture. More formally, the function is going to say, under a policy, what is the collection of rewards that you can get? Okay, and those rewards could be random. So that's why there's an expectation here. So you can say, hey, if there's a good policy, so yes, let's say the policy is fixed. So that's why the subscript pi here. Given a policy, like you can interact with the environment according to that policy. Something's transpired. There's some random rewards come up. You get to some random new situations or states and so on, whatever, and eventually you perhaps exit if it's a maze setting from before. But what is the expectation of those rewards, cumulative rewards, starting from that state? Is going to be the value of that state. So of course, if you're very far away from the exit, you have a lot of rewards, but they're also discounted. So maybe the value is going to be not as high as being right next to the exit. Although there are not too many steps involved, there's no discounting. These gammas are, by the way, discounting factors. And so perhaps the value is going to be high. Okay. So let's look at an example, right? So here's an example for maze 1. I think in the 2 slides ago, I said you get an immediate reward of -1. Every time you take a step, if your step doesn't involve exiting, then you get a reward of -1. So the more time you spend in the maze, you're kind of doing badly. Okay. So under that way of like rewarding, you can see that if you're right next to the goal, the value of being in that state is the highest, actually, the least negative. Okay, -1. The further away you're moving away from the goal, the worse and worse your value is. Like you should try to avoid these states. And this one is the worst, so you should definitely try to avoid this state. So there's somehow quantifying the value of being in a state under a policy, which is an interesting metric. Okay, so far it's not yet an algorithm, no nothing. We'll see how to convert these ideas, this basic building blocks, a policy and the notion of a value function. We'll mix them up and see how they can be used in an algorithmic approach later. Okay. Any questions about value function? Okay. So the last component, and this is where the learning part comes in, and learning part comes in, which makes it reinforcement learning and not just planning or just decision making. Okay, is the idea of what is this environment, right? So do we already know about the environment, everything about the environment, or do we have to do trial and error? Okay, so far as we've been talking about, we have to do trial and error. We don't know what the future state is going to be. We don't know what the reward is going to be. That's why we want to try to learn and do exploration, exploitation, and so on. Okay, but what if we can represent the environment using a, we are using the generic word model here, but what does model really mean is that it's the description of how the environment works, right? So here the model really means what is the way, model really means these two equations here. Okay, there's a lot of symbols here, but all it means is that given in a state, if your current state is little s in value and your current action is little a, then what's the probability of you reaching state S prime? Okay, it's just a conditional probability, right? So because the environment at the end of the day is also going to do the same thing, right? If environment says I'm in current state S, if the agent gives me action A, I'll tell you what the next state is going to be. That's what the environment's job is. And so if you know exactly what this conditional probability is, you know about the environment. This is a model of the environment. Similarly, if you're in current state little s and your current action is little a, there's a distribution of rewards. The expectation of that, if you know already, then you know everything about the environment. You know, on average, if I'm in this state, I'm going to take this action. This is the reward I'll get, and these are the states I can get to with different probability. Okay, so in that case, I don't need a separate environment. I don't need a simulator. I don't need a real world to kind of figure out what to do. If these numbers are known for every state action pair and all, for all input outputs, basically for all little s's and little a's and s primes, then I know everything about the environment. There's no need to learn anything, right? So it's not like I need to learn, if I take action A, I might get to some state S prime. I already know if I take action A and a little S prime, then what is the distribution of next state I'll reach, right? So there's nothing to learn. So if you know the model, then you kind of just have to do planning, okay? Just decision making. Now, one way to do RL, which is actually comes back to last time when I was saying that you don't have to mix learning and decision making all the time. So you could always collect a lot of data, do your forecasting, build a forecasting model, build a prediction model, and then you can take decisions. Okay? You can do in 2 steps, right? Same thing here. So you could have an RL approach where, hey, first I'm just going to do which is what A/B testing was, by the way. You're just collecting data first, and then you're figuring out what action is a good one. Here, what you can do is you can just say, hey, forget about cumulative regret, forget about rewards. I'm just going to do whatever in every state just to kind of learn what is going on. Okay, what am I going to learn? Just the model, a proxy, like a proxy for the environment. Once I learn the model, then I can just solve some sort of an optimization problem to figure out what is the best action to take in each state. Okay? So you can have an RL approach where you can say, hey, for the next 3 hours, I'm just going to do random exploration in my state. Let's say if I think of a robot situation, maybe it's a little bit more visual, random explorations. And then after 3 hours, given the data, that's going to represent my model. Given that model, I'm going to just solve some optimization problem, and then I know what to do in every state. That's one way to solve RL, but it's a very inefficient one, just like A/B testing is an inefficient way to do things. But this is an integral component in the sense that this is related to the value function definition, and those two obviously are related to figuring out best policies, and things like that. Any questions here? We'll see an example here, right? So what is the model? Right? So model is very simple. So if you go, if you're in some state, let's say this, as I said, each brick is a state, each square is a state. If you say I want to go east, right, or to the right, then you just go to the right. So there's the probability of, if you're saying if you under one brick, if you want to go right, then what probability with which will go to the right brick? 100% probability, unless you add some noise. And then what's the reward you're getting in irrespective of what action you take? -1. So it's a very you already know everything about the environment, so there's nothing to learn if you already knew this beforehand. But if you did not know how the maze will give you reward, And if you did not know if you took a right action sometimes because maybe there's wind, whatever, like it could be like a game situation, so you might not end up where you wanted to go, and so those things you will have to learn, right? So any questions here? These are the three very baby, I guess, building blocks using which we can start thinking about formalizing like how to plan and then how to learn and plan together. So, okay, what is the time? Yeah. So what we'll do next is kind of understand a formalism or I guess again, a language to kind of plan. And that language to plan will kind of help us define a approach to reinforcement learning. Okay. So first step, we'll kind of just think about planning. And to do that, we'll introduce the notion of Markov decision process. There are three words. I will disambiguate all three words. Process, I already told you. Process just means a collection of random variables for us. Decision is all about actions, and Markovian means exactly as I said, future is independent of past. But all three words together, it's unclear what is going on. So, but we'll kind of disambiguate that. Okay. And then kind of come back to this value function idea again. So what we're doing is basically what we said just before: policy, value function, and model. We're going to relate them together. Okay? We're going to relate them by again ignoring this whole learning and earning or learning and decision making business for now, because we just have these building blocks. Let's try to relate them together. And one way to relate them together is through MDP framework, Markov decision process framework. Okay. And then we can address the question of optimizing, which is just planning. And then we can talk about actually learning and planning. Okay. So the way we're going to do this section is, again, going to be very interpretable and very gradual. First, we're going to talk about what is a Markov chain. Okay, Markov chain is a, we'll see what Markov chain is, but as it says here, Markov chain is just the state transitions happen autonomously. So the simplest object, Markov chain. Then we're going to introduce one additional thing, which is rewards. And so it's going to be called a Markov reward process. And then we're going to introduce actions, and then it becomes a Markov decision process. So this hopefully kind of, our goal is to really understand what is the Markov decision process and what is the value function. Remember, what is the value function? What is the policy? What's the model? How are these three related? MDP was going to tell us how it's all these three are related. That's the last part. But to do that, we'll do these baby steps first. Okay, let's understand what a Markov chain is. When there is no actions, no rewards, something. And then once we introduce rewards, there's something else. Once we introduce rewards and actions, it's the MDP. And then we can see the connection between policy, value function, and the model. Okay? And model of the environment. And the same model, just, it's model of the environment. Okay, so what's the Markov chain? Okay, this is the, how many of you have heard of Markov chain before? No? A little bit, okay. So it comes up quite a bit in machine learning, although because of the dominance of deep learning these days, people are not looking at Markov chains, as much as maybe 5-10 years ago. But it's a very important part of, for example, Bayesian machine learning. Okay? Very, very important computational gadget for doing Bayesian machine learning. And Bayesian machine learning is important when you want to be aware of uncertainties. Like you want to know when you're making a prediction how uncertain you are about the prediction, right? So anyway, so Markov chains are very important. But in our context, what is a Markov chain? Right? Markov chain is just a collection of random variables which have Markovian dependence between them. So Markovian dependence just means that the probability of the next state taking the value s prime, given the current state value taking s, is a number, p s s prime. It's a number, a parameter. And this conditional probability is basically saying that, okay, this conditional probability is, I didn't write the Markovian property here, but basically it's saying the idea is that if you introduce additional or previous random variables like st minus 1, st minus 2, st minus 3, they don't influence, they don't change this number. So it's just past is independent of the future, which is st plus 1, given the current most recent past or current. Okay, so that's the this is one number which characterizes one state transition from S to S prime. Okay. Now, if I have n states, let's say 10 states, yeah, 10 states, then I can, since there's one number per state transition, there are 10 states. So you can transition from state 1 to state 1, state 1 to state 2, state 1 to state 3, state 1 to state 10. So you will generally think of in terms of like something called a transition probability matrix. Okay, so this matrix here is a matrix with a bunch of numbers, and it captures everything about the Markov chain or a process. Chain just means a process, by the way. Ignore the chain if you're confused. Okay. So this matrix completely characterizes this matrix and the initial, I guess, state distribution, as in what is the initial state, completely characterizes this Markovian process, this stochastic process. Okay. In fact, this matrix, all it's doing is just accumulating all these conditional probabilities. So the first row is just saying, hey, if you're in state 1, what's the probability you'll go to state 1 itself, state 2, state 3, state 4, state n. Okay, it's just the conditional probability of going to some other state starting from state 1. Second row is saying, starting from state 2, what's the probability you'll go to some state? Okay, it could be the same state, it could be other states. That's all. That's all. So it's just a row-wise. The row sum is 1. Basically, so it's just probability mass functions just stacked one below the other. Okay. And in this example, if you can go from every state to every state, so we'll see an example here, right here, where you can think of these as states, the circles as states, and then the arrows just represent, hey, if you are in the state, let's say class 2, then with 0.2 probability you'll go to the state sleep, 0.8 probability you'll go to state class 3. So they sum to 1. If you're in class 2, then the only thing you can do is go sleep or go to class 3. Okay.
So just to clarify, like the matrix that you showed on the last slide, the n would represent all of the available states to go to.
Yes. Yeah. So these are all the states, 7 states here.
So it wouldn't just be like a fixed matrix of seven states. Like if we were at class 2, there'd be 2.
No, there's one matrix for the entire thing. So if you're in class 2, then you look at the second row and you kind of see, oh, I can only go to class 3 or sleep. Yeah. And the sleep state is put as a square only because there's no outgoing arrow. So if you sleep, you don't. That's the end of the kind of that day. So there's no outgoing arrow here. So there's some details, by the way. I'm being very hand wavy here. Yeah. Yeah, here's an example, right? So you could start from, let's say your starting state is class 1, you can go to class 1, class 2, class 3, pass and sleep, or you can go to class 1, Facebook, class 2, and so on. So these are just realizations, trajectories of realizations, and each one you can call it an episode. Okay. So sleep is the ending episode. When you hit sleep, you stop. So it's called an episodic, I guess, Markov chain, compared to Markov chains which go on and on and on. Okay, so for example, weather phenomena or something, they are all, there's no end relatively. So here, there's an ending state. Okay, so these are not, these are certain class of Markov chains. Okay, and where there's an end state. Any questions here? Just an example of, okay, there are some states and some transitions happening. So 7x7 matrix parameters. In fact, this is a matrix. Yeah. And you have to also tell what the starting state is. Maybe class 1, you fix it as class 1, or you can have a distribution over the states as, okay, what is the potential starting state? Okay, so the next idea is to introduce rewards. So Markov chain, there's nothing much going on. All I wanted to say was there's state transitions and there's some parameters that capture the state transition. What we're building towards is that those state transitions essentially are like kind of a model of the environment. Environment has to jump from state to state, but it's not really an environment because there's no actions yet, and the environment should also spit out rewards. So we're going to introduce those two parts. by first introducing rewards because that's pretty easy. So a Markov chain with rewards is just, it's called a Markov reward process. All we're doing is that every time you transition, just emit a number, just report a number like a random variable, some number, which kind of signifies a reward value. Okay. So what are we saying? So every time you do a transition, what is happening here? Oh, because of this chair. Yeah, every time you transition, so let's say you go from S to S prime, you were at state S. So let's say you emit a reward. Okay, so emit a reward with the expected value R subscript S. Okay, so every state is associated with an expected reward, or every state is associated with a random variable, and you just take an expectation, and that parameterizes this process. Okay, and you also, one additional thing we define is the discount factor gamma. Okay, discount factor, just think of it as a number between 0 to 1. So let's say 0.9 for simplicity, for our understanding. Okay, so this is an example of a definition of a Markov reward process. It has a bunch of states. So those, let's say 7 states, the script P matrix, which is already like the 7x7 matrix. In addition to that, a bunch of these reward numbers, like the expected reward values, for example, and one additional number, which is a number between 0 to 1. Okay, let's say 0.9. So why did we add these rewards, extra rewards, is to kind of now talk about, at this stage, we can already talk about what is called a value function already, okay, without even introducing actions. Although with actions also we can talk about value function. So first, we're going to introduce one intermediate quantity, a random variable, which we're going to call it as a return random variable. Okay, it's just a name, return random variable. What is it going to be? It's going to be just the sum. So a random variable at time t, it's going to be just sum of rewards that you collect in this Markov chain. So as the Markov chain, as you go from class 1 to class 2 to class 3, for example, you're changing states. Each state you would also get a number. Just add up those numbers. Okay, and you'd add up those numbers by also adding a discount factor. Okay, so in general, if the numbers are like it's going on forever, then you'd have a summation from 0 to infinity. But if it's an episodic thing, you would stop at sleep state and whatever the number you got at that point, and that's the last number. Okay? So this gamma is just taking care of the fact that if you had an infinite situation, then gamma is ensuring that the numbers don't blow up, the GT number doesn't blow up. Okay, so if each of the intermediate numbers, if each of the reward is bounded as in like, each of the reward can only be at most $1. And if gamma is less than 1, then the summation cannot go to infinity, even if you sum all the way to infinite time steps. Okay, so this is a random variable because just the sum of a bunch of random variables. So it's just a random variable. The expectation of this random variable, starting from a starting state, is called the state value function. So, so you're at the starting state, let's say class 1. And then from there, the Markov chain is just going class 2, class 3, maybe Facebook, maybe something else, and then hitting the sleep state. Okay. So there's so many potential possibilities. Take the expectation. So each of the possibilities will lead to different rewards. Take the expectation of that summed up reward random variable, which is called the return random variable. And that's going to give the value of being in that state. So value of being in class 1, value of being in sleep state, value of being in class 3, and so on. Okay, so that's the return random variable. So that's the state value function, sorry, which is the expectation of the return random variable. Any questions here? It's going to be an interesting. So let's look at the example. So here, again, it's the same idea. So you have the states. They're just, you can jump around. It's the same matrix from before. Only thing that's happening is that in every state, you can just have them expected reward, like -2, -2, -2. If you pass, +10, sleep, there is no reward, and so on. So it's just one number associated with each state. Okay, and there's a discount factor also. So you can see that this for the same sequences that we saw before, like C1, C2, C3, pass, and sleep, there'll be, okay, if you're in C1, you get a -2 value. Sorry, -2 as the immediate reward. And then you go to C2 and you get a -2, but you have a discount factor of 1/2, and so on. So you, in the first trajectory, your summation is like a discounted sum, except it's ending at sleep state, and that's the discounted sum. Okay, so you got a discounted sum of the return random variable realization took a value -2.25. In the next realization, you had something else. Instead of going to class 2, class 3 immediately, you went from class 1 to Facebook, and then class 1, class 2 sleep. Okay, so that had a different rewards that you realized, and you do a discounted summation, and you got some number. Okay, so you get all these realizations. Remember our which is just this equation here, and remember our state value function starting from the state C class 1 is just going to be an average of these guys. Okay, just an expectation of these guys. So being class 1 is perhaps -3 or something. Any questions here? Okay. Now, that's a discount factor, gamma. So 1,4 is like gamma square. To keep the summation finite. I think I didn't put the second term. That would have been even nice to kind of show you. But yeah, this is like a r plus gamma r t plus 2 plus gamma square rt plus 3 and so on. Why do we need that? Because if there's an infinite summation, that gamma will ensure that the summation doesn't explode. Okay. Anything else?
Is there, I'm building on gamma, is there like an instant or like closer gratification?
Yeah. So yeah, this I don't know if you've done a finance course. There's a time value of money, right? So this is just time value of reward. So you don't really care about further rewards. You care about the immediate reward. You can interpret it that way as well. Yeah. So at the Markov reward process discussion itself, we can actually identify a very interesting, we can make a very interesting observation, okay, which is that the value of a state is linearly related to values of other states. It's a big, it's actually a very simple observation from just a definition, but nonetheless, it's a very important observation that kind of drives many algorithms that you'll see. I mean, we'll only see one, like Q-learning, and we'll kind of just pattern match that maybe this is something going on over there. But a very interesting observation, right? So the value function of a state, V of S, you'll see that, if you don't look at the three or four equations there, if you look at the last line, it's related to the value of being of other states also. So if you think of this expectation, just think of this expectation as summation, right? All the potential future states you can get to from this state. Let's say from this state, you can go to 3 other states. Then this expectation is all it's saying is what are those 3? Like the expectation is saying with some probability go to, the next state being S prime, the next state being S double prime, the next state being S triple prime, double prime, triple prime. Then this is just saying that the value of that state is related to the value of those 3 states. Okay, that's in a linear way. Expectation, if you remember, is just a linear operation. Linear operation just means it's a summation going on, pretty much. Okay, so how, actually you can see from these equations how it is, but value of a state is just the expectation of the return random variable, right? Given the starting state is S, little s, right? This S is this little s. That's just by definition. First equation is by definition. Next, we just say plug in the definition of GT, which is the return random variable, which is just the RT plus 1 plus gamma RT plus 2 plus gamma square RT plus 3 and so on. This is just the definition of GT, right? Next, what we do is a very simple trick, which is that RT plus 1 plus you take gamma common across all these other guys because you can, because gamma is common factor for all the other terms. So you take gamma as a common term, then you get RT plus 2 plus gamma RT plus 3 and so on. Okay? Then is a step where this summation is nothing but GT plus 1. Okay, so far we have not done anything smart. It's just definition, extracting and factor out, and then calling it GT plus 1. Okay? Nothing has changed. This is true for any trajectory also. But what is interesting is that at this step to this step, what we're doing is this expectation is actually expectation over all the random variables involved in the bracket, right? So it's an expectation over RT plus 1, expectation over GT plus 1. Okay. What we can do is that we can see that GT plus 1 related random variables don't involve RT plus 1. So GT plus 1 is by definition RT plus 2 and so on. So it doesn't involve RT plus 1. So you can take that part of the expectation and actually apply that expectation immediately on GT plus 1. And that gives you this expected value of GT plus 1, which is V of ST plus 1. It's just that we don't know what that ST plus 1 would be. Is it S prime, S double prime, S triple prime? That's why it's a random variable here. Okay? For any one of those, we know what the expectation of GT plus 1 is. Okay, so that's why this is um, the value of the next random state, which is capital ST plus 1. Okay. So anyway, all this wordy thing, as I said, the highlight of the slide is just saying that the value of a state is related to value of other states. In fact, in a linear way. Okay. So that kind of gives ideas on like how to compute values if you know the model, as in if you know the environment and so on. It's just planning related things. You can get some ideas on how to solve. Okay. But yeah, let me skip this slide because it's the same thing what I mentioned with diagrams. So that was an interesting fact with Markov reward process. Now what we want to do is actually add actions also back, add actions into the picture. So we had the Markov chain, we added rewards, we got a Markov reward process. We're going to add actions now. And now it's not going to be anymore a Markov chain. It's not going to autonomously change states. Actions will influence the next states. Okay. So what we introduce new is in red. So what we introduce is a bunch of finite set of actions. It can be infinite also, but we'll just look at the simplest setting where the number of actions is like finite. Like a joystick can only do a few number of moves, right? So all we're changing in this now conditioning how the environment behaves is that it also gets influenced by the action that you take. Current action in the current state influences what potential new states you'll get into. Okay. Now it's no more a matrix. It's not a Markov chain matrix that we had before. Now it's going to be some sort of like a tensor because you have to condition on a state, condition an action, then you get a distribution over next states. Okay. Similarly, the rewards, you can think of a matrix if you want, but basically given the current state and given current action, there's some random reward and the expectation of that is this function script down. Okay. So then the discount factor is the same as before. Finite number of states is the same as before. So here's an example, right? So here, the notation has changed a bit in this diagram. So your actions are now Facebook, study, and so on. Okay, so those are actions. The circular ones, we're not going to ascribe them any state names here. Okay, and if in this state, if you study, you'll go to some other state. Okay, that's what this figure is trying to say. Or in this state, if you sleep, you'll go to that state. And in this state, if you go, there's one new action here. In this state, you can either study or you can go to pub. Okay. So there are two actions you can take here. And even here, you can take either sleep or study. Here, you can take Facebook or study. So there are a couple of actions available in each state. Okay. And when you're in Facebook, so when you're in this state, you can either continue to use Facebook action. You also have two actions here, sorry, or quit Facebook. And so you can come back to some state. So the states themselves don't have names here, but the actions can kind of tell you what's going on. But if you take the pub action, you get reaching a kind of a state where there's no particular action you can take. You can just, irrespective of what you do, you'll just end up with 0.4 probability somewhere here, 0.2 probability here, 0.4 probability here. It's just to kind of show some difference. Okay. So any questions about this example Markov addition process? Okay. So now that we have introduced actions, we can now talk about policies. Policies are now going to be what is the action? What is the action you're going to take in each state, or what is the distribution of actions that you define in each state? Okay, that's what a policy is. Okay, and a policy is going to completely define the behavior of an agent. Given a policy, actually it's in the next slide. Given a policy, we can go back from Markov decision process to Markov reward process. Okay, so what do I mean by that? Given an MDP, which is this collection of objects, and a policy, all we're doing is once the policy is fixed, then we know exactly what actions are going to be taken in every state. Okay? That's what a policy is, right? Even if there's randomness, we know exactly how we're going to behave in every state. Okay. Because of this, the state sequence comes back to being a Markov process. Okay, it becomes a Markov chain, the state sequence. If you fix a policy for a Markov addition process, the state sequence is just a Markov chain, and the state and reward sequence is just a Markov reward process. So the nice thing, all I'm trying to say is that although we introduced actions, if you predefine the policy, if you there could be many policies at every state, you could do many different things. So there could be many policies or functions, but under every policy, you just have a Markov chain and or you just have a Markov reward process. Okay, so now it's becoming a little bit more clear. This value function, you can define value function under a policy is nothing but exactly what we just saw from Markov reward process, just the expectation of the return random variable under that policy, because there's nothing, no further, it's completely autonomous. There's nothing else to decide. The policy is already telling you what actions are going to happen in every state. Okay. Okay, so let's not worry about this notation. This is kind of trying to capture the stochastic policy situation. So there's a summation of our actions. But let's come back to the return random variable and the value function. This is kind of important. This is somewhat new. Policy we have seen before. It's just a function from state to actions, and so we can kind of relate to it. Now value function, right? So as I said, a Markov addition process under a policy is just going to be a Markov reward process, which means there is a value function we can define. Okay, and so that's exactly what we're doing. What we're doing here, v subscript pi just means that hey, we are in the Markov addition process setting, but we have defined, we have already said like some policies that we're going to use. Under that policy, the value function is just going to be the expectation of the return random variable starting from the state S. Okay, following the policy pi. Okay, so this just nothing changed except we added a subscript pi, because under pi is just a Markov reward process, and we know exactly this is the definition for value function. Okay. But in addition to that, we can actually define another value function. Okay, which is what actually is a teaser, gives the Q in the Q learning approach, okay, or algorithm, which is a value function called the action value function or the state action value function. Okay, it's just definitions of functions, no learning going on. We don't even have an algorithm, nothing. This is just building blocks, right? So the state action value function or the action value function is exactly the same as the equation here, except I have an extra degree of freedom. Okay, so in the bottom equation, my function's input is just the state. In the bottom equation, at the top equation, my function input is just the state. Bottom equation, it's the state as well as some action that, as well as the initial action. Okay, so there's an extra degree of freedom. So here we are just saying that hey, starting from state S, keep applying pi of S. Pi of S is the policy, that's the subscript. So keep applying pi of S from the get-go. In the bottom equation, we're just saying, hey, if you're in state S, take, you give me what action to take. It could be pi of S, or it could be something else. And then from next state onwards, we'll keep applying pi of S. Okay, slight difference. Okay, and that slight difference is, because if you're not going to use pi of S, for example, if A is equal to pi of S, then Q pi of S comma pi of S is nothing but V pi of S, is what I'm trying to say. So these two are just slightly different versions of each other. Okay? And this Q is just a symbol that people chose, and so that's why that Q transformer and Q learning and all that, it's the same Q. Okay. Any questions about these two value functions? Just definitions so far. Okay. So just like we saw earlier, that the value function in the Markov reward process had this recursive, had this relation that the value of the state has is related to value of state other states. Okay, that's called also recursion. Okay, especially if time is increasing, right? So, for example, V of S, remember, is related to V of S plus T. This is the equation that we saw with the Markov reward process. All we're doing in this equation is put a subscript pi here. Okay, so this recursion can also be written for the slightly varied value function, the state action value function. Remember, where the only difference is that we have a degree of freedom of what is the initial action that we can choose. Okay, there's initial action that we can choose. Now these two equations both are called Bellman expectation equations. Okay, and are very interesting recursive equations, which in computer science, if you've heard of dynamic programming, okay, they're related to that as well. Okay, so dynamic programming is related to these types of recursive equations. Okay. So these are the And why am I pointing these out is because these recursive equations inform both how to solve the planning problem when your model is known, when you don't have to learn anything. These equations help you define an approach to solve the planning problem. And these equations also kind of are inspiration for algorithmic approaches for the learning and planning problem, which is the reinforcement. So you may say, hey, what is so informative about this? I don't know if I have a slide here. Yeah, let's, I mean, we'll take a break in a second, but this is the same slide. Actually, let me not use this slide. Yeah, just look at this equation, right? Even here, I can just explain the same idea. So let's see, how does it inform the planning problem? It's gonna be like this, right? So if this, look at this equation, right? So this equation is telling you what is the value of a state, and it's linearly related to value of other states. Okay. Now, if you wanted to compute the value of a policy, so value of states under a policy pi, okay, like if you actually wanted to compute it, okay, how would you do that? How would you do that is, let's say, to compute the value of a state or value of all the states under a policy, if you already know the policy, how would you do that? If you should also obviously know the model of the environment. Let's say we are in the planning setting. Okay, we're not learning anything. Which means that we know what the transition probability is, as well as what is the reward given a state and an action. Okay, if you know that, it turns out this is just an equation, and you can write this equation for every state. Then what you get is a system of linear equations actually. Okay? This is a linear equation, by the way. There's no, it's expectation just summation. So you just think of if you think of v pi of s is like x1, then there's some x2, x3 involved here. So it's just a bunch of, it's like ax is equal to b type of a system. It's a system of linear equations. Okay, so you can just do a inverse b and figure out what the x's are, as in what the values are. Okay, if you knew the model. So that's one way to. So this is not completely solving the planning problem, but it's showing you how to get the values for any policy. Okay, so that's a. It turns out that computing the values for any policy is a stepping stone for finding the best policy. I don't know if I should say that right now or. Yeah, let me actually mention that, because there's nothing more going on than the expectation equations. So there's just this slide is just saying, okay, if you knew the value function, how do you define what? We can use the value function to define what is the best policy. Remember at the beginning of the slide deck, we were saying, oh, we want to find actions which maximize our total reward. The total reward is actually what the return random variable is capturing, right? The random variable is literally reward plus reward plus reward plus reward. And the expectation of that is the value function. So we want to find a policy that maximizes the value starting from some starting state. Okay, so let's say some starting state, I have a value for every policy. I want to find the policy that maximizes this value. Okay, so let's call that. We don't know what the policy is. I mean, in fact, the policy is going to be the optimal policy. Let's call it the optimal policy. Whether it's unique or not is not a big deal. And let's call this number. Okay, which that optimal, under that optimal policy, there's going to be some value for the state. Let's call it the optimal state value function. Okay, so for every state under the optimal policy, there's going to be a value for that state, right? Let's call it v star of s. And similarly, under every state and and an action, there's going to be the best value that you can ascribe to that state and action pair. Let's call it q star of s, q star at that state action pair. Okay. Now it turns out that and this is, by the way, just stated as a fact, we are not, unlike Bellman expectation equation, where we knew just because of Markov reward process, it is actually true. And by just putting extra pi subscripts, it's still true. Here we are not proving anything. Okay? This is called Bellman optimality equation. This is just stated as a fact in this slide deck, which is actually, I don't know if I have it. Yeah, which is that the optimal state action value function. So the optimal state action value at a pair s comma a is related to the optimal state action value at another pair s prime a prime. It's just that the relation is not linear. You can also change this expression to v if you want. All I'm saying is v star of s is related to V star of some other S values or S primes, whatever, in a non-linear way. Okay, and that's why it's called the Bellman optimality equation. And it's written in a with respect to Q's, it's written here explicitly, where Q star of S comma A is related to immediate reward in that state and taking that action, plus gamma times what all new states you can get to, which is all the S primes from that state, and if you took that action, times Q star S prime A prime, where A prime is the max over Q stars at that state S prime. Okay. Now this is just taken as a fact, no proofs, no kind of intuition of why this is true. But turns out this is true. It's a non-linear equation because of the max operation here. Okay. If there was no max operation here, then it will not be Q star. You can just put Q pi here, and that would be exactly the Bellman expectation equation. The max gives you that extra non-linearity. So if you could solve the system of nonlinear equations, which is involving Q star, if you could solve it, okay, we know how to solve system of linear equations. Just Ax is equal to B. We know how to solve it. But if you could solve this nonlinear equation, then you can actually find one of the ways to find the optimal policy is this way. If you solve the nonlinear equation, you get all the you get all the Q stars. Then the best action to take in every state is just going to be, hey, look up the Q star value and keep changing the second argument, figure out what is the second argument which gives the highest Q star value. That's the best action to take in that state. Okay. So in that state, the action that you want to take is, this is just a distribution. So it's saying put all the probability mass in that action, where that action has the highest Q star value among all the actions you can take in that state. Okay. It's just all we're trying to say is that Bellman optimality equations involve some nonlinear equations and relationship between Q star at some state action pair to Q star at some other state action pairs. If you could solve the nonlinear equations and somehow get handle on Q star, then your optimal policy is just given by Q stars. Okay, very simple way. Okay. Now what we've done is, if you knew the environment, then only you can solve the Bellman optimality equation, because that equation involves expectation and rewards and so whatnot. If you don't know them, you will not have that system of equations, and so you will not be able to solve. So if you know everything about the environment, there's no learning, then you have a system of nonlinear equations. If you could solve it theoretically, then you know what the optimal policy is. So it's still non-trivial. The planning problem is non-trivial still, because you have to solve the system of nonlinear equations, which you don't know how to do. Okay, or there are ways to do it, but they're not just system linear equations, for example. Okay. So the planning problem without learning part is still, or decision-making problem is still non-trivial. Okay. Yeah, any questions here? Okay. So let's take a break and then resume at 7:45. Sharing. Yep. Okay, so I know we rushed through a little bit over there. What we'll do next is actually spend some time on algorithm, and an algorithm which is called Q-learning, and actually see an example implementation of it, so that it's pretty concrete, like what's going on with respect to most of the concepts that we've seen from before the break. So as I said, what we're trying to do is like approach this last part, which is come up with an algorithm for reinforcement learning, which is before the break, I was just talking about, oh, there's this notion of state action value functions, and they satisfy Bellman expectation equations, and the optimal ones satisfy Bellman optimality equations, which are a system of nonlinear equations you can get if you enumerate it for every state. If you could have solved it, then you get the best policy. That's just, but to solve it, you need to know the environment. You need to know the model of the environment. And so that's what we kind of ended before the break. So now let's think about try to not think of just planning. We want to try and actually solve the exploitation. So we have to learn and figure out a policy. Okay, figure out a policy or figure out a good set of actions to take so that we can collect as much reward as possible. So that's what we're going to do with the last step, which is Q learning. So to do any of this, first of all, we need to know how to, to do kind of to do well. You need to be able to estimate well, and then kind of know how to improve yourself, right? So very vaguely speaking. So what is estimate well is exactly how do you compute Q pi of S comma A. So for any given policy, let's say we're doing some sort of like an iterative approach where we have some current policy, we want to slightly change it so that we can get to improved policy, and so on. And for every policy, remember our objective function was for any policy, we can if we can know Q pi of S comma A or V pi of S, then that kind of gives us how good the policy is, because let's say S is the starting state, then we really want to maximize. We want to figure out best policy, which kind of gives us the highest number, okay, from the starting state, right? So what I'm trying to say is that to find the best policy, you have to predict Q pi really well, and then you need to know how to go from pi to pi prime, pi to improved functions. Okay, and that's true for whether you're doing planning or reinforcement learning. Okay, and it turns out again, we're not going to get into details, but Q learning does these steps behind the scenes so that it can do that improvement in the learning plus decision making setting, learning plus learning plus planning setting. Okay. So I just wanted to point this out, that any algorithmic approach should handle both, estimate well what you know currently and also know how to improve yourself, right? So that is kind of essential ingredients. So let's actually directly jump to the algorithm, because it's pretty mechanical, very intuitive, and builds on epsilon greedy that we've already seen last lecture. And then we'll see how it actually works in the example setting in code, so that it's more concrete, like what's going on. Okay. What is the algorithm? So it's based on Q values. It's in fact based on maintaining Q of S comma A, estimates of Q of S comma A, and just iteratively improving them. Hopefully the estimates are as good as or as close to Q star of S comma A, because if I know Q star of S comma A, I know what the optimal policy is. Okay? So what I'm trying to say is that if I can, in fact, I'm going to describe the algorithm in a situation where I only have fixed number of states and a fixed number of actions you can take in each state. So like the 7-state example in our illustrative thing a few slides ago, sleep and so on, right? So that one only had a few number of states, right? So let's say we have few states and few actions to take. Then what we're going to start with is a matrix. Okay, why is it a matrix? Our Q function is just a function of two inputs, state and an action. So it's basically you can represent that function using a matrix. Okay, and we're going to start with this table or a matrix where every cell represents what is the Q of that state and that action. Okay, which we don't really care about Q of S comma A at any given pi or anything like that. What we actually care about is getting the Q star of S comma A. Okay, so hopefully that table, through some iterative process, through learning and exploitation, hopefully that every cell in that table converges or gets close to Q star of S comma A. Okay, that's the aim. Okay. So what we'll see is some variation of the online machine learning loop that we have seen last lecture. So start with some starting state. Let's say we fix the starting state to be some starting point. Let's in the grid, maze example, you have to start from somewhere, right? You start from the entry point. Okay. For every round, what you do is you see the current state and take an action. Okay. I didn't say exactly see the current state, but see the current state, what state you're in, and take an action. Okay. What is that action going to be? Take an action uniformly at random, or pick a random action basically with some probability. That's the exploration. Okay. So far it looks like as if we are doing just epsilon greedy, but the next step is we're going to rely on the table that we have. Okay? So the current at any given point of time, we'll have this table with some numbers filled in. Maybe they're off. They could be completely, they could be good estimates. They could be bad estimates of Q star, but whatever. There's some numbers there. in the exploration, if you're doing the explore action, we're taking a random action at random. If we are doing exploitation with some other probability, which is the remaining probability, then we're going to look at the table, look at the current state we are in, which means in this table, it's going to be a row, the current state we are in. There's going to be a bunch of actions that we can take. We're gonna take the action that has the highest Q value. So in that row, whichever is the index of the highest value, that index, whatever action it corresponds to that column, that's the action we're going to take. Okay, that's exploitation. So what are we exploiting? That exploitation. This is called exploitation only because we're thinking of, okay, this Q values are good enough that we are actually know in that state what action to take. Remember, our optimal thing to do if we had Q star is exactly that. If we have Q stars in every cell, then in a given state, you just have to look at what are the, let's say, 4 actions that are possible, and whichever action has the highest Q star, that's the one you play. That's the one you take. Okay, that's if you remember from 2 slides ago, this is what you do. If you knew Q stars, every row in that state you are in, which is a row, whatever the action that leads to the highest value, that's the one you play. Okay? That's the one you take. So at least the action choice is clear given the current Q table and looking at the current observation. So if you think of the online machine learning group, observe the current state and take an action. So those 2 steps are clear. After that step, you collect a feedback, right? Based on you given your current action, you get a reward. Okay, you collect the feedback. And the next step is going to be looking a little bit messy, but the next step is just going to update the table. In fact, update 1 entry in the table. That's all we're going to do. We're going to get a reward, RT plus 1. That's the kind of setting here. But with RT plus 1 and current state and some current action and so on, we're going to update an entry in this Q table. Okay. So how do we update Q? Okay. The update in Q is going to be like the gradient descent type of a process where there's going to be old Q value and there's going to be some new Q value. So the old Q value is on the right hand side. Okay, this is the old Q value, and I'm going to update it to some new Q value. Okay, which cell am I going to update? The cell at which the current state was and where I took certain action. Okay, so if I was in state ST, which is where I took the action AT, then that's the cell I'm going to update based on the reward I observed. What is the reward I observed? That's this RT plus 1, which the environment gave me. Okay. So this is the old value. It's being updated. It's being updated with this extra correction term, basically. So it's like some sort of a perturbation or some change in the old value, right? With alpha t as some sort of a multiplicative constant. It resembles very similar to like a gradient descent update. Remember, there's alpha t there is called a learning rate. Here also, it's called a learning rate. Okay, or learning constant. And this term inside it's defined as temporal difference error. Okay, temporal difference mostly because it's a difference between what you think is the value of being in that state and taking action AT, which is Q of S comma A. Okay, that's the value, right? That's literally saying what is the value of being in a state and taking action A, right? That's a kind of an estimate of the value, if not the value itself, versus what is the value you will estimate from going to the next state and collecting the reward. Okay, so the difference is, so ideally, these two should be equal. Okay. What do I mean by that? So let's go back a few slides. If you look at this expression, Q star of S is equal to the reward that you can get from that state plus some sort of average of the rewards, average of the Q stars that you can get in the next state. Okay, a max of that actually. Okay. If you look at this expression, this right hand side actually resembles this expression here. Okay, so R plus gamma max of Q at the future state is exactly the right hand side in that Bellman. I mean, it's not exactly the same, but like it kind of resembles the right hand side of the Bellman optimality equation. Okay, so all we're saying is if there's an error, the error is basically that we thought Q if the Q table had exactly Q stars, and they were exactly the Q star values, or the optimal Q values, then this term here is exactly equal to this term. Okay, so there's no correction to make, which means that Q star is equal to Q star plus 0. Okay, but since we're not at Q star, the old value will be adjusted to kind of capture this temporal difference. The temporal is because we are talking about t plus 1 related values here and a t related value here. Remember, t related value is the st, and t plus 1 related values is st plus 1 and rt plus 1. Okay, so somehow this temporally different quantities, different way of computing quantities, they ideally should be the same if the Q table had the optimal values, but they're not the same. So there's a difference, and that difference, some weighted value of that difference is being adjusted to the old value to get us a new Q value. Okay. Now, another way to look at this is that if you notice on the right hand side, there's Q of ST80 here. There's also Q of ST80 here, right? So what you can do is that bring those two together. Okay, then the coefficient in front of Q of ST comma 80 is going to be 1 minus alpha t. Okay, so 1 minus alpha t times old value plus alpha t times some new information. New information is RT plus 1, which is the new feedback that we collected. So it's just a moving average of some weighted average of the old value plus alpha times some new value, which includes new value, which is this expression with the reward. Okay, so that's another way to think of what is the update doing. Update is kind of dragging the Q value to better, it's including rewards, but some weighted value of the rewards as a part of its estimation. Okay, but really the motivation for this iterative update, okay, there's an iterative update because for every time step, whichever location, whichever cell we are in, kind of we update that number, is really driven by the Bellman optimality equation. Okay, Bellman optimality equation and Bellman expectation equation both inform the planning problem, as I said, because for the planning problem, it's just a system of nonlinear equations. You can solve it somehow, then you can get the optimal policy. It also informs the learning plus planning problem, which is a reinforcement learning problem. Okay, where you can see that these expressions here kind of look like the terms in the Bellman optimality equation. Okay? Remember, the end goal of Q learning is to keep updating this table and make actions, take exploration actions according to that most recent update by doing the appropriate balance between exploration and exploitation, and collect as much rewards as possible in terms of cumulative rewards. Okay. And this algorithm is shown to kind of work really well to do that, to collect for total rewards. It can also learn the optimal Q values. Okay. What do I mean by that? So let me come back to this. It turns out after long enough time, if you keep applying this exploration strategy, after long enough time, this Q matrix or the Q table will have entries equal to Q star. Okay, so you're just doing this greedy exploitation at every time step, and because you're doing this type of nice update of balancing new information and also looking at this temporal difference error and so on, which are also which are essentially kind of part of that Bellman optimality equation. It's natural to think of like this update equation and exploitation are ensuring that the entries of this Q table kind of get closer and closer to the Q star. Okay, if that is the case, if you're getting closer and closer to Q star, you're basically going to be acting optimally. Your action is going to be optimal, right? So because your action is going to be exactly this, which is the optimal thing to do if you had Q star. Okay. The alpha t, just like as I said, is called the learning rate, or inspired by the gradient descent kind of interpretation. And epsilon is the exploration parameter. This is very similar to our epsilon greedy approach. Okay. So any question about this algorithm? So this is the algorithm, but this is what kind of underlies all the advancements that you saw with Flappy Bird, with Breakout, with even self-driving and other videos that we've seen in the past couple of lectures. All of them kind of inspired by this approach. Not all of them, but like a good chunk of them, at least the Flappy Bird and the breakout example for sure. But there are other algorithms also which are now popular. Okay. So there are many routes to kind of figure out what is the best thing to do in each situation. Okay. Or what is how to collect more and more rewards. One of the routes that the Q-learning algorithm takes is via the component of value function, or in particular state action value function. You can also say, hey, I don't care about value functions. Can I directly optimize for just the policy? Can I just improve policies as I do exploration and exploitation? That is also possible. That's also potentially going to be a reinforcement learning algorithm. And there are some policy-based methods, okay, which really just rely on the policy building block and learning that. And so there are some methods which use value functions, and there are some methods which use both. Okay? But there are multiple methods to kind of approach reinforcement learning in general. But the ones that you saw with Breakout and Flappy Bird, they're based on this. Okay, and Breakout is actually an example of like the 2012 improvement in RL, as well as perhaps, no, actually, maybe in AlphaGo there were some slight differences. But yeah, in the Atari games improvement that Google DeepMind showed, it was actually this algorithm. Actually, this algorithm plus convolutional neural networks to interpret the screenshots. Okay, to define what the state is. State is going to be some sort of the screenshots, some transformation of screenshots. Okay, so what I want to do is I can spend more time on interpreting like why Bellman optimality equation is leading to this type of update. But instead, let's assume that this is the algorithm template, and I'm gonna just go through some code just to kind of ground a few more things that we saw today. Okay. So that code is present in our repository. Before getting into the code, I just want to quickly mention this repository called Minimal RL, where they show multiple RL algorithms. Okay, so Q-learning itself is not there here because it's kind of captured in this thing called DQN, which is deep Q learning, which mixes Q learning with deep neural networks, which is actually the approach taken by DeepMind 11, 12 years ago. So, but there are many others. Okay, so there are different names, and you can see that there are only actually like 60 lines of Python code for one of the algorithms is like pretty good, right? So I would just encourage you to, and it's already set up for a certain environment. It's called Cartpole, so you can try and play with it if you want. Cartpole is this environment where you have to balance the pole for as long as possible by moving left and right, like breakout kind of. So let's actually jump to a different an implementation detail. Okay, so this is a repository called machine learning katas. I think I don't have is there a link here? Yeah, maybe there's a link. Actually, there's a link here. You can click GitHub. Okay. So we're going to look at Cliff World and again, just reinforce what we saw about different components and then look at Q-learning also a little bit. Okay. Just in terms of implementation, it's not complicated. So I wanted to spend some time on this. So Cliff World, okay, what are we trying to do? So what we are trying to do is to make a robot kind of avoid the cliff and get to some destination. It's like a maze, but like a simpler maze where the robot, so this is now, we're going to not talk about planning. We're just going to talk about learning plus planning in the sense that robot doesn't know where the cliff is. And if I fall off a cliff, I'm going to lose points and stuff like that. The robot doesn't know it. So it has to do trial and error and eventually figure out how to get to a destination and actually reap rewards. Okay, so that's what we need to do. So that's the illustrative figure here. Any questions about what Clifford is? I'm going to explain it again. Let me connect. So what's the difference between that page and this page is that this page, this page, we have a code in our repository, which has the same thing, except the difference is that that page is the question. This page also has the answer. So answer being the Q-learning implementation. Okay. So what, as I said, so what we're going to do is understand the environment. Again, we're going to it's basically a recap of what we did through this lecture today. So we're going to set up the environment, we're going to set up the agent, and we're going to make them talk to each other. And we'll talk about what is going on in this environment and what's random strategy look like, what's how does Q-learning do. Okay? So bunch of imports, I think, given so much of it is like not very useful at this point. So let me mention them later. So setting up plots. So here is so from the cartoon, from the illustration, here's the specific representation. This is like illustration of the environment, just like we did it in the slides. Okay. So there are 4 rows and I guess 12 columns. And the cliff is over here. Okay. This edge between -100 to -1 is the cliff. Okay. So the robot is starting at location 0, 0, and it has to reach 0, 11. Okay, so it just has to reach from this green block to this black block. And how does it reach? So the fastest way is obviously to kind of go through this, but it's a bad idea because the cells represent what is the reward that you get if you're in that state. Okay, so if you are in that state, you get a reward of -100, which is pretty bad. So ideally what you should do, the best thing you could do is just step down, go all the way to the right and step back up. Okay, that's the best policy if you know everything about the environment. Okay. How do you deduce that best policy? As I told you, if you don't want to kind of get too, if you want a general purpose kind of agnostic algorithm, not specific to grid world, then you should just rely on Bellman equations, Bellman optimality equations. So for example, these numbers here represent the immediate reward. And you can just write a system of nonlinear equations with Q star of being in the state 0, 0 and taking an action left, 0, 0 taking an action top, 0, 0 taking an action down. For each one, there's going to be a relation between that Q star and other Q stars, which you don't know a priori. That's why it's a system of nonlinear equations. Solve the system of nonlinear equations, then you can actually get what is the best thing to do, which is exactly go down here, go all the way to the right, and go back up. So that planning problem is doable, very mechanically without knowing, cliff world and all that motivation. But just as long as you can define Q of S comma A, in terms of Q of S, other S comma A's. And that's Bellman optimality equation actually defines Q star of S comma A with Q star of S comma A at other places. So the equation is kind of universal. You can use it for any location to just plan if you know the environment. Okay? But we're going to be in the reinforcement learning setting, so we don't know the environment in the sense that the robot has to sometimes fall off the cliff quite a bit. And in that sense, it's quite challenging, right? Even if it learns, okay, there's something bad here, and figures out to come over here, maybe here or some other location, it might try to go back there. And first of all, by falling so many times, it doesn't know that there's actually an end where it can actually end the thing and get the highest non-negative reward, cumulative reward. Okay, so there's a lot of challenges if you want to, if you don't know much of the environment, you have to do trial and error. So it says the agent begins each episode. It's episodic because once you fall off the cliff, it's like the sleep state. You don't, it's the end of the episode. Okay? You start on the green square, and each time step, you move one step. You can't leave the board. So when you are at the edges, you can't go left and right appropriately. And the 2 ways in the episode, you get to black or you fall off the cliff, right? So this is the online machine learning loop or reinforcement learning loop. You observe something, you choose an action, environment changes the state. They're written in a different way where you observe at the last step, you observe the new state and get the reward. Okay? So that's the loop. Okay? I don't know which one did I execute. Did I execute any cell? Actually, I should execute. Oh my, okay. So let's not assert this. Let's run all. Okay, while we discuss this. So here's a very crude way of writing the entire thing. There are actually packages which give you these environment definitions, which are easy. Like at the end of the day, what does the environment should do? If you give an action, it should tell you what the next state is and what the reward is, immediate reward is. That's it, right? But here we are kind of explicitly kind of writing down what the environment API is. So we are enumerating all the states 0, 0 all the way to 0, 11. 3, 11. Actually, let me just write it. And then which states are the bad states? The first 1 to 10 are the bad states, right? Between the pink and the black blocks. What's the gold state? It's a very natural way to define this environment. What are the states available? What is the bad states? What are the good states? And what's the final state and what's the beginning state? Okay. And then every other reward is -1 and cliff reward is -100. Okay. And what are the moves possible? Here they have made it in a very nice way, textual, where less than arrow and greater than arrow represent left and right, and similarly B and this cat symbol they represent north and south. Okay. So what are the reason why they defined it this way is so that they can do easily manipulation of if it's not, if it's the current state value is like 2,3, then how if you go north, then it's like it should be 1,3, for example. You can do that. So these are all the parameters, what states there are, and all the other things. What moves are possible, state action, the Markov MDP definition, basically. What is possible. Okay. And then here's the, I think it's just the same figure, just plotted here. Okay, so now given that primitive, you can put that in the, you can define the environment. It's called the cliff world environment. Initialize with all the, actually we are not inserting all that, but okay, so here we are inserting, if we want to record what all steps the robot took, and what is the positions that the robot has touched. We just want to get a sense of this, because that way we can differentiate between two policies, a random policy and a Q-learning based policy. Okay, we're going to look at if we can look at basically this is just logging. Okay, so here's the API, right? So new state is going to be state m plus move m comma state n plus move n. That's why we define states and moves in terms of those numbers, so that we can just add them, and that's going to be the new state given a move. So given in a state, if you take an action, what's the next state? That's one part of the API. And given a state, what's the reward? That's the second part of the API. Okay. So if you are in the cliff states, then the reward is that's it, -100. But if you're not in the cliff state, then your reward keeps adding up, or -1, whatever you get, it keeps adding up. Okay. Sorry, reward is just that, but you also help yourself. I mean, you can also record what is the cumulative reward you're getting. Okay? The reward is just either you're in really bad state, which is you're fallen down the cliff, or you're in less bad state, which is you're not at the goal yet, but you're not fallen down the cliff. Okay? And each terminal and logging is just things. So here are valid actions, right? So this is the boundary cases where if you are already at the if you're already at the boundary, which is that because all state tells you what are the valid numbers possible, like only 0, 0 is possible. You can't go 0, -1, for example, or you cannot go 0 to 0, 13 or 0, 12. So that's what we are checking. If those sums, they're falling outside this collection of explicitly enumerated state values. Okay, it's invalid state. So here's a run for a random agent. What is the random agent doing? So this is now environment is defined. All we have to do is interact with it. Now, how do we interact with it? Should we interact intelligently or not? This is like the A/B testing type of thing, right? You're just randomly trying action A, action B, and you don't care about the rewards, right? So here is the random action, right? So you're just picking whatever the number of actions possible. So sometimes valid actions are only 2, right? If you're at the bottom left corner, then you can only go east, or you will only go north. You can't go, south or west, for example. But typically you may have 4 actions, 2 actions, whatever. So among the number of actions available, pick anyone uniformly at random. That's what we're doing here. So I mean, you don't have to do this. You could have just done numpy.choose, for example, and you would have gotten the same type of thing. And learning, there's no learning. You're just accumulating rewards. I mean, it doesn't matter. So the learning part, you didn't have to do anything, because actions are not influenced by anything that you're collecting. So here's the instantiation of that agent. So instantiation of the object from the class, and similarly instantiation of the domain. And now once we instantiate the domain, so when we instantiate the domain, we pass all the parameters, the state, pairs, and all that stuff. Okay. And running the episode is just while you have not reached the terminal state in this experiment. So domain is like an experiment here where while you have not fallen off the cliff or you have reached the end goal, you pick up what are valid actions possible, tell the agent to act from these valid actions given the current state. The agent will say, oh, I'm in the state. These are the only valid actions possible. Let me take some state action, and then give that action to the domain. So it'll tell you what the new state is and also what the reward is. And optionally, you learn random action. Random agent doesn't learn anything, so that can comment out if you want. And then keep moving. Okay, so this is just a while loop. We know that it's not going to be infinite while loop. It could be, but it's not going to be infinite while loop. You will either fall off the cliff or you will reach the end goal. Okay, so and there's some helper function for retrieving some data and plotting it. Let's not read that. So here's the path of an random agent. It directly fell. It first thing it took is just take a right. So okay, maybe we should run it again. I don't know if it's still running, but shift enter. Oh, it's still the same. Oh, I'm not changing anything, is it? Let's try again. If it's not changing, yeah, it's I don't know. Maybe it's just a random. So many tries of the same thing. Okay, let's actually move to Q learning. So I'll not explain all. I mean, there's some blurb of exactly what we discussed in the lecture. But let's go down to what are we trying to do, right? So we have some Q values. This is exactly what we saw in the slide. So we start with some Q table where rows correspond to states, columns correspond to actions, and we start with some starting state, which is the pink block. We take some action according to highest Q value, or we take a random action depending on yeah, here we just say, so this is not 100% correct. So we have to do exploitation. And then once we observe the reward, then we have an update step. This is exactly the same as in the slide deck. Okay, so there's nothing new going on. Okay. So here is the Q class, Q agent rather than the random agent class. And what you need to see is like the action, right? So how do you act? So you flip a coin. This is what I'm doing. You flip a coin. Stats.inform.rvs will give you a sample from 0 to 1. If that value is greater than epsilon, you do one thing. If the value is less than epsilon, you do something else. Okay, what is the one thing? You can either act randomly, remember exploration, or you can act greedily, which is the exploitation. Okay? Those are the two things you can do. And the learning is, I guess, it's left here, but I've already coded it, which is Q of S comma A new is Q of S comma A old plus alpha times the temporal difference error, which is exactly what we did. So temporal difference error is actually right here. Is just figure out the, temporal difference error is actually reward plus gamma, the discount factor, times the maximum Q value minus whatever the current Q value. Right? This is exactly, just in code form what we saw in the slide deck. Okay. And then run experiment is exactly the same as before. I mean, okay, here it's actually learning. So we are not seeing because there has to be trial and error. We're not going to look at the trial and error performances because they're also, many times it will fall off the cliff. We are not seeing that. After the trial and error, hopefully it has collected enough reward. We're not focusing on the reward here, cumulative reward, but we'll see what after that amount of learning, the Q table hopefully corresponds to reasonably good Q values, which is like closer to Q star, which means that hopefully it knows how to go all the way to the goal. Okay. So it's learning. So we're not, plotting that. So we ran it for 500 episodes, so 500 trials and errors. So basically it died like 500 times or 499 times. Okay. And in fact, even the last episode, it did not do well. It actually only, actually it did well. It did not fall off the cliff. -17 is good. Okay. So here's the visualization. It's very similar to before. So here's the policy. Okay. Now this again, we are seeing it very similar to how we saw in the slide deck for the maze. So what is this policy, right? What is the visualization? Every cell, we are doing two things. One is capture the value of being in that state. And also, what is the policy that after doing the Q learning, we've learned. Okay, so the symbols indicate exactly are we going top, left, what is the policy suggesting? Okay, so you can see that. So first of all, let's focus on the policy itself. Policy saying come down, and then it's immediately saying go here. Actually, here it's saying come down and stuff. So optimal policy we know, right? So optimal policy is like this: go all the way to the right and go back up. Okay, so here what it has learned is, try to, it has learned to go back. For example, here, if you're here, then go down. So somehow it has learned to kind of avoid the cliff and then go up here, like really being conservative, like go all the way up to here and then go up. There's nowhere else that it's saying go up. Okay, so I hope you can visualize like what's going on, right? So after doing all these trial and errors, it's saying go. We have to go left. Sorry, we have to go right. But we have to we should only go to the top, either at all the way to the right side, or it's getting confused. We might have to go up here is what it's getting confused, and it thinks that this is a good value state. Okay, this is just the artifact of the number of simulations and so on. And the value is like darker means better value. So because it's negative number, so here you're in worse values. Sorry, including the worst values being lightest color here, like C off the cliff is going to be the lightest color, so worst values. And then if you're not off the cliff, then you're darker, so you're better. This is the best state to be in. Okay, and here there's no need to evaluate because it's a goal. So this is the best state to be in, and you can backtrack and see these are all worst states to be in. So yeah, so here's the final episode. There was some logging code in the script. So this is the final thing that it did. It did not immediately do all the way straight. It went like this, and like this, and collected -17 as the points for this navigation. Okay. Any questions here for this code? So, I mean, in reality, for any realistic application, you can't do this. In the sense, you can't enumerate states and you can't keep a Q table. And that's where the whole thing about having a neural network, which is what DQN and DeepMind did 10, 12 years ago with Atari games and even with Flappy Birds. Actually, with the Flappy Bird demo, I think we did enumerate the states, but with Atari games and AlphaGo and things like that, you don't enumerate things. You just use CNNs and other deep neural networks to kind of do some processing beforehand. Okay? So that's something we have not touched on. But this toy situation, you didn't have to even think about, only by telling the reward signal, the algorithms figured out what is the best way to get from point A to point B. Like your only reward signal, you predefined, hey, don't fall off the cliff. On the cliff, you're good. Off the cliff, you're bad. And the more time you spend getting to the destination, the worse you are, like -1 kind of capturing that. By just defining the reward signal, you're able to make the agent do the task you wanted it to do, which is go from starting to the goal. Okay. Okay, so that's about it for the code. And so the code is available in the experiments examples directory. So you can play around with it and change things if you want. So I'll not give the intuition. Yeah. Let me just summarize. So RL is a framework for kind of making agents intelligent. And in fact, just wanted to mention that there is actually I don't have it here. So TensorFlow has a tutorial on multi-arm bandits. And there they use the word agents also. So agents is an overloaded word. I mean, many different fields use the word agents, including large language model subfield. But here we just mean like agents mean the person who needs to do explanation, exploitation, and plan, and so actually learn and therefore make decisions, right? So RL is a great framework to do that if you are in the sequential decision making setting. If you get the opportunity to do trial and error. And all the designer has to do is not pre-specify what the optimal policy is. Just as long as you can give reward feedback through a simulator or yourself, then the agent will figure out what's the best thing to do, or what's the best sequence of actions to take. Many problems still remaining. We don't have the next lecture for this, but there are many applications, realistic applications where something like this can be used. Not just reinforcement learning, but also contextual bandits, as we saw in the MSN.com example, but also multi-arm bandits, which are also used for A/B testing and various things. So all of these are very prevalent today. Yeah, so if you have any questions, let me know. Otherwise, we'll stop here. No questions? Okay, let's stop here.